Hello, Physics 360 students. Welcome to Electricity and Magnetism, also called E&M. This is the first of what will probably be a number of videos I'm going to do throughout the semester to provide additional information that will be helpful in our study of E&M, but which I won't necessarily use class time for. And the first video that I'm going to talk about with you is content that I think will be review. A lot of it will be review for you, which is one of the reasons I'm doing it in a video. Specifically, I'm going to take the very beginning content of the textbook we're going to use in this class. This is the very well-known E&M textbook that is used throughout the country, Introduction to Electrodynamics, 4th edition by David Griffiths. Absolutely want to have your own copy of this book. It is an invaluable resource for any physics or astronomy/astrophysics major. And chapter 1 of Griffiths' book is like a mini Math 210 course, multivariable calculus. And the chapter is called Vector Analysis. Analysis is a fancy word for doing calculus. And we're going to be spending time talking about calculus using vector functions. But before we can do calculus, we have to do algebra. So I want to review vector algebra in this video. Specifically, Chapter 1, Section 1 in Griffiths' book, Vector Algebra. Let's start with the basics. Of course, when we say vector, we can have, for now, our Physics 110 introductory physics understanding of what a vector quantity is. Right? We tend to think of a vector as a quantity that has both a magnitude or size and some kind of direction associated with it. In motion, the common vector quantities, of course, are displacement, velocity, acceleration, force, linear momentum, angular momentum. Those are the common ones you come across in motion. In electricity and magnetism, there are still is going to be force. That will be very important. But probably the most important vector quantities are the electric field and the magnetic field. And those will be the topics of our study all semester. But we'll take a vector to be anything with a magnitude and a direction for now. And how do you do algebra with vector quantities? Add, subtract, things like that. We're going to start with geometrical thinking with vectors. And that means we're not choosing any particular coordinate axes to be looking at these vectors on. They're just existing in up to three-dimensional space, the kind we're used to, called Euclidean space. And so, let's start by adding and subtracting two vectors. As you know, the common graphical way of representing a vector quantity is an arrow, where you draw an arrow and the length of the arrow is representing the magnitude of the vector, and the direction the arrow is pointing is the direction of the vector. All our drawings here will be confined to two dimensions. So we've got our two vectors as represented by the arrows labeled A and B. Now, a word about notation that Griffiths uses, I'm taking these figures from Griffiths' book. Vector quantities in Griffiths' book are bold letters. But what we're going to write in our class notes, what I'm going to write on the board, and what you're going to write in all your homework and quizzes and tests when you are representing a vector quantity is the symbol, like an A, with an arrow on top. That is how we are going to represent a vector quantity. For the simple reason that when you're writing on paper or on a screen, to denote something as bold type, not very convenient. So, when Griffiths writes a symbol like this, that's a bold capital letter A. What he would mean by the way we're going to represent vectors is that, capital A with an arrow on top. And of course, we know he's thinking of it as a vector because he's drawn it with a magnitude and a direction with that arrow. And he's going to add that vector A, whatever that physical quantity is, it's a vector, to another vector quantity, B. Right there. And he's drawn those two vectors in what's called tail-to-tip configuration, meaning that the tail of B is at the tip of A. And then the rule for adding those two vectors to construct the vector A plus B is to draw a vector from the tail of the first vector, A, to the tip of the second vector, B, right there. And you have added those two vectors. That is the vector sum A plus B. Note that the magnitude of A plus B is not the magnitude of A, that would be the length of the A arrow, plus the magnitude of B, the length of the B arrow. That would be scalar addition. Vector addition is different from scalar addition. And we must preserve this rule, the tail-to-tip rule for adding vectors. The nice thing about the tail-to-tip rule, by the way, is that it can be used for the sum of more than two vectors, 3, 4, 5, however many. Just put them in tail-to-tip configuration, and the resultant, the sum, goes from the tail of the first to the tip of the last. Now, one nice thing about addition of vectors is that it is what's called commutative. Write that word out. That means the order in which you add two vectors doesn't matter. I can take vector A and vector B and add them as A plus B, and that's the first drawing I just talked about. I can take the same two vectors, but add them in the reverse order. I can start first with B, that's B again, and then follow it with A in tail-to-tip configuration, and then draw an arrow from the tail of the first to the tip of the second, and that will be B plus A, not A plus B, B plus A. But then look at the arrow B plus A and the arrow A plus B. They have the same magnitude and same direction, they're the same. So the order in which you add the vectors does not matter. So that's written symbolically like this. A plus B equals B plus A. Okay, and that's true for any number of vectors that you're adding together. 3, 4, 5, 6, however many. It doesn't matter what order you add them, which is nice. That's not going to be true for all vector operations, so enjoy it while you can. Now that's addition. What if I want to subtract one vector from another? What if I want to take the vector A and subtract from it the vector B? In the course of solving physics problems, we may need to do that algebraic step. We definitely will. How do you do it? What is the rule for doing that? The rule is quite simple. It's still actually vector addition, basically. You take the vector A and you add to it the vector negative B. Now, what is the vector negative B? It is exactly the same as the vector B, except its direction is exactly reversed. And that's shown in this third picture over here. We're going to take A minus B. So first we'll draw the vector A, same A we've been using in all of these figures here. But then remember what the vector B was like? It was pointing to the right. So the vector negative B has the same magnitude as B, but points to the left. Just reverse the direction of B, and you have negative B. Now, A and negative B are tail to tip, and now add A with negative B. So, draw an arrow from the tail of the first to the tip of the second. And you've constructed A minus B instead of A plus B. So there's A minus B. And you'll note that that arrow is not the same as the A plus B arrow. So adding the vectors, subtracting the vectors, gives different answers. Okay, now that's the geometrical way to add and subtract vectors. And we have to be aware and understanding of that method. Here's something else we can do in vector algebra. We can take any given vector and multiply it by a scalar. Now let me get you used to that notation. If I use the symbol A, make it that way, I want that, for a vector of a certain magnitude and direction, there it is, there's A, and we want to multiply it by a scalar, I will, using your author's notation, represent a scalar as just a regular italicized letter. Doesn't matter what letter it is. I happen to use little a here. Could be any letter you want, but no arrow on top. Okay? And that represents any kind of a scalar. So what we're doing here, in terms of a multiplication process, is we're multiplying the vector by some scalar, little a. What happens to the vector? Okay? Well, you get a new vector where the magnitude of the new vector, magnitude, is the magnitude of little a, because that scalar you used could have been negative, times what we call the magnitude of the vector that we started with. That's my way of denoting the magnitude of a vector. Put the absolute value symbols on it. Okay? So if the little a magnitude is bigger than 1, the new vector you're going to get by this multiplication by a scalar has a bigger magnitude than it did before. So for example, in the drawing over here, we multiplied the vector a, big A, by the scalar 2. And all that did was give us a new vector with twice the magnitude of the original one. Okay? Now, it could be that the scalar you're multiplying by is negative. Instead of taking big A vector and multiplying it by the scalar 2, like this drawing shows, what if we took big A vector and multiplied it by the scalar negative 2? What do we get? Well, we just get another arrow, another vector. I didn't draw that very well. See if I can draw that better. With magnitude 2 times the magnitude of big A, but reverse direction compared to 2 times big A. Now, what if the scalar you're multiplying the vector by, the little a in this formula, is less than 1? Let's say it's positive and less than 1. Let's say it's 1/2. What do you get? You get a new vector with a magnitude that's 1/2 of the original vector. So that would be something like this. Right? That would be 0.5 times big A. Like that. So all you do is multiply the magnitude of the vector by the scalar. And if the scalar is positive, you don't change the direction. If the scalar is negative, you reverse the direction. Okay, so that's multiplication by a scalar. Another operation we will have to do with vectors, very important, is ways to multiply two vectors. Now, I talked right there in the previous slide about multiplying a vector by a scalar. And that is a multiplication operation you do in vector algebra. But what if you have two vectors? How do you multiply two vectors together? Now, it turns out there's more than one way. The first way, we have to know both of them. The first way I want to talk about is called the dot or scalar product of two vectors. Scalar product tells you what you're going to get out of this product of two vectors. You're going to get scalar. Dot product is probably how you remember the name, and that name is given because the kind of operation we're talking about is denoted symbolically like that. Where you take two vector symbols, in this case a vector A and a vector B, and you just put a dot between them. And when you write like that, you are telling your reader, hey, I am taking the dot or scalar product of the vector big A with the vector big B. So a standard picture you see then when you talk about dot product of your two vectors is the one that's drawn here. The vectors A and B lie in a plane, the plane of the screen in this case. Any two vectors together form a mathematical plane. They are drawn with a common tail. That's very convenient when you're doing dot product. And then there's an angle theta, that is the angle between them when they're drawn with a common tail. Okay, with that in mind, here comes the definition, 3 lines, of the dot product of 2 vectors. Okay, this is how it is defined. Take the magnitude of the first vector. Notice how I'm denoting magnitude. Capital A, arrow, absolute value. Scalar multiply with the magnitude of the second vector. And scalar multiply that with the cosine of that angle theta between the 2 vectors. Magnitude of the first times the magnitude of the second times the cosine of the angle between them when they're drawn with a common tail. Okay? That is the definition of scalar product. One way to think of it geometrically is if I were to take the projection, as it were, of the vector A along the direction of B, that would be, let me draw that, right there. That would be that arrow I just drew in red is the projection of A along the direction of B. And that projection is from trig, magnitude A cosine theta. So what the dot product is for these two is the projection of one vector along the direction of the other, such as the projection of A along the direction of B, that's this part here, times the magnitude of B. You're taking the projection of one vector along the direction of the other times the magnitude of the other. Now, when you do the dot product of 2 vectors, you can get a result that's a positive scalar, you can get a result that's a negative scalar, and you can get a result that's equal to 0. It really boils down to that cosine theta and how big the angle theta is. The angle theta could be 0, which would mean the vectors A and B are actually pointing in the same direction. I'll draw them side by side like that, but the key thing is they have the same direction. That'd be the angle theta 0. That's the biggest you can get for A dot B. You could have the vectors A and B be exactly perpendicular to each other. That's a very important case. I'll draw them like that. And that meaning a right angle there. Then you're taking the cosine of 90 degrees. Do you remember what that is? The cosine of 90 degrees is 0. So when the 2 vectors are exactly perpendicular to each other, their dot or scalar product is 0. Oh, that's really important. Or the angle between the A and the B could be more than 90, all the way up to 180. We won't tend to need to have angles bigger than that. And then the cosine theta is negative. And so the A dot B will be a negative scalar quantity. Okay, so those are some important things to remember about the sign, S-I-G-N, of the resultant dot product of 2 vectors. It could be positive, it could be negative, or it could be 0 if the 2 vectors are exactly perpendicular. This definition of dot product tells us that it doesn't matter whether you write A dot B or B dot A. That doesn't matter, because it's just magnitude of the first times magnitude of the second, cosine of the angle between them. That's all that matters. Okay? All right, so that's a commutative property. A dot B equals B dot A. Don't take that for granted. That's not going to be true for every kind of product of vectors. Here's a helpful one. The scalar product is said to be distributive. So if I have this configuration, A dot into the quantity B plus C, certainly an operation that might occur, you can distribute the dot through the parentheses. In other words, you can write this as the operations A dot B, and you can use parentheses if it helps you to see the pairing, plus A dot C. We have distributed the dot as a vector operation through the parentheses. Okay? All right, what do you get if you take any vector and you dot it into itself? You could ask what you get, right? Well, use the definition. That's magnitude of A, scalar product with the magnitude of A, times the cosine of this angle we're calling theta, which is the angle between the two vectors when they're drawn with a common tail, but the two vectors are both the same, A. So the angle between them has to be 0, right? So I'm taking the cosine of 0 degrees, but the cosine of 0 degrees is plus 1, so that's what that's multiplying. And so this is just the magnitude of A squared. That's what you get when you multiply any vector with itself. Its magnitude squared. Okay? All right, let me show you one little cute trick, and then we're going to talk about the vector product. Let's take the vector A and the vector B, just like we've been doing, and let's also construct a third vector, C, where C is A minus B, okay? Or A plus negative B. What would that look like for these vectors? Well, let me see if I can draw them. I'll draw them over here to the side. There's the A. That's my way of drawing the arrow for A. There's the B. And C is A plus negative B. And one way to think about that, of course, is the way I drew in the slides up above. But another way is to just look at this, mentally rearrange it. If C equals A minus B, then C plus B must equal A. And so that will tell me that C actually points from B to A, so that C plus B points to A. So those are the three vectors, A, B, and C, where C is A minus B. Let's take those as given. Given those three vectors, A, B, and C, which is A minus B, let's calculate the dot product of C with itself. Now we know that that will be the magnitude of C squared. That'll be the length of this side of this triangle squared. Note, by the way, that angle right there is what we're calling theta, right? Between A and B. But then this is also A minus B dot A minus B, right? C is A minus B. But the dot product is distributive, so we can distribute the dot between both of those sets of parentheses. That means we'll have A dot A minus A dot B minus B dot A plus B dot B. All right, I just used the distributive property of the dot product. Okay, so I'm getting an expression for the magnitude of C squared here. Note I have here A dot A. Any vector dotted with itself is the magnitude of that vector squared. So that's the magnitude of A squared. And we have B dot B here at the end. So but that's the magnitude of B squared. So let me write that one next. Plus magnitude of B squared. And then minus. And then I have an A dot B and a B dot A. But the order doesn't matter in a dot product. So A dot B and B dot A are the same. They're both negative, so we'll do negative 2 times A dot B. But we just wrote up above what A dot B is by its definition. It's magnitude A, magnitude B, cosine of the angle between them, in this case theta. All right, now look at what we've shown. For this triangle right here, formed of the three vectors A, B, and C, with the three sides, and one of the angles there labeled theta. C is the side then opposite to theta. The length of that side, C squared, is equal to the lengths of the other two sides squared and added minus 2 times the length of the other two sides times the cosine of the angle theta. If you don't recognize that, that's the law of cosines, which can be handy in vector algebra. We just proved it, right? We just proved the law of cosines, just from simple properties of vector algebra. Okay, in this video, I want to talk about one more kind of operation, one other way to take two vectors and do a product of them. Now, whereas the scalar product, also called the dot product, of two vectors resulted in a scalar, this second method of multiplying two vectors is going to result in another vector. So it's a little bit more complicated. And it's called the vector product of two vectors. Again, we'll use A and B, like we've been drawing there. And the way we denote a vector product is with the cross symbol. And so this is often called the cross product of two vectors. Remember that? A cross B. And they're the two vectors A and B drawn with a common tail, and there's an angle theta between them. And they've even drawn the outline of a parallelogram that the two vectors form. That would certainly be true. Any two vectors form a mathematical plane, and when drawn with a common tail, you can sketch out a parallelogram formed by them. Well, they form two sides of a parallelogram. Okay, so what's the definition of the vector product of two vectors, A cross B? Just going to state it. You take the magnitude of the first, A, scalar product with the magnitude of the second, B, times the sine, watch out, sine of the angle theta between them. Sine, sine, sine. But that can't be all, right? Because that's a scalar expression I've written. The cross product of two vectors results in a vector. So I need some way to denote and to be clear on what the direction is for this resultant of A cross B. I will just use the symbol that Griffiths uses, n hat. Any symbol, letter, with a hat on top, we call a unit vector. The hat is the key thing that tells you it's what's called a unit vector. A unit vector has magnitude 1, or unity, no units, and this has one job, merely to point in a particular direction. So what is the direction of this n hat unit vector that is the resultant of A cross B? Well, it is the unit vector that points perpendicular to the plane of the two vectors A and B. In this case, A and B lie in this screen. So n hat must be perpendicular to the screen. That's what we mean by the n hat in this case. It's perpendicular to the plane of A and B. But wait a minute. If the plane of A and B is the screen as we see it, there are two directions that are perpendicular to the screen. Out of the screen and towards us, or out of the screen and away from us. That's an ambiguity. So which do we use? We all agree to use the following rule. It's called the right hand rule, which I know you remember. And the way the right hand rule works is you take the fingers of your right hand with your thumb extended as if you were hitchhiking. And you reach in and you, with the fingers of your right hand, you push the first vector of the product, A in this case, on top of the second vector in the product, B. And so when I do that with my right hand, push A on top of B, I have to do it such that my thumb would be pointing into the screen. Okay? So in this case, for these vectors, and doing A cross B, n hat is directly into the screen. We denote a vector pointing into the screen, by the way, as an X with a circle to imply that you're looking at the back end of an arrow. Okay? All right, now that's A cross B. Note something important. The cross product, or the vector product, is not commutative. In other words, the order matters. If I were to do B cross A, I would get exactly the negative of A cross B. Reversing the order of the two vectors in the cross product gives you a negative sign. And that follows from the right-hand rule here. So if I do B cross A, and apply the right-hand rule, now I've got to push B on top of A. Don't do A on top of B, B on top of A, and your thumb points out of the screen. Okay, so B cross A is out of the screen. We represent that as a dot with a circle around it to represent the tip of an arrow coming at you. So be careful, in a vector or cross product, the order of the vectors matters. One thing that is helpful and is the same as in the dot product is that the vector product is distributive. So in other words, if I have, back to blue here, A crossed into a parenthetic expression, let's say B plus C, then I can distribute the cross operation through the parentheses. So this is equal to the cross product that the result that I get when I do the cross product, A cross B, added to the result I get when I do the cross product, A cross C. So that's important, and that's helpful to know. Okay, here's the reason that little parallelogram is drawn. It's because the magnitude part of A cross B, which is this formula, length of A or magnitude of A times magnitude of B sine theta, is the area of the parallelogram formed by A and B. And that's because if you take, say, A sine theta, that's that length, perpendicular, and you multiply that by the length of B, that is the formula for finding the area of a parallelogram. Take the base times the altitude or height. So that's geometrically what the magnitude of A cross B is. It is the magnitude of it's the size of the area of the parallelogram formed by A and B. That's useful. Here's one other useful thing to remember, very useful thing to remember. If you take the vector product of any vector with itself, remember we did the dot product of a vector with itself? What if you do the vector or cross product of a vector with itself? What do you get? You see what the answer has to be? It has to be 0, right up there from the definition. If I'm taking the cross product of A with itself, then that theta, the angle between A and itself, is 0, and I have a sine theta in the formula there, and the sine of 0 is 0. Okay? You can think of that 0 there as the 0 vector, which by definition is a vector with magnitude 0. But it's very helpful to remember that. The cross product of any vector with itself is 0. In fact, the cross product of any vector with another vector parallel to it is 0. Because any two parallel vectors have an angle between them of 0, and the sine of 0 is 0. Okay? Okay, so this is our first lecture on vector algebra. It's going to be a couple more, doing this in stages. Okay? But hopefully this is mostly review and will be helpful for you to get up and running in Chapter 1. That's all for this video.